Hello guys, how are you again? Today we're going to continue our lessons and we're going to talk about properties of alkanes and other hydrocarbons. So we said in our previous lessons that we have the alkanes or the hydrocarbons that are made of only one single bond and we call them alkanes. And we said that they depends on the number of carbon atom inside the compound to know how to name this compound. Now those compounds guys are the physical properties for them mainly depends on the molecular mass of the compound. Because if you look at the compounds here, they are all made of carbon and hydrogen, which is a nonpolar covalent bond. So in molecular compounds that contains only nonpolar covalent bonds, we will find only the weak type of intermolecular forces, which is London dispersion forces, which is a very weak forces. So it is the only thing that will affect the physical properties. As you can see here on this table, if you look at the first four compounds from methane to butane, you will find that they are gases. Look at the boiling point at the room. You will find that butane boils at 0.5 Celsius. So at the room temperature, which is 25, it's going to be a gas. So methane and ethane, propane and butane are gases in the room temperature. And as the number of carbon atom increases in the compound, you can see that the boiling point for the compounds also increases. This is why pentane and octane and decane are liquids at the room temperature, which is 25. As you can see, the boiling point for pentane is 36.1 and it is 125.7 for octane, while it raises up to 174.1 to decane. And even more, if we talking about more complex compounds, for example, heptadecane, C17 or C20, you will see that the boiling point is increases to reach 300 or 350. So they are going to be solid in the room temperature. So remember guys, the main factor that affect the physical state is the weak London dispersion forces inside the molecules. And by talking about the first four compounds, which are methane, ethane, pentane, and butane, we call them a natural gas, which is a fossil fuel composed primarily of alkanes containing 1 to 4 carbon atoms. So, mixture of those four compounds considered to be natural gas. And these alkane are gases because they are very small molecules, as we said, and they have the weak London dispersion forces between them and are not held together tightly as the larger alkanes does. Now, if we're going to talk about the other compounds, of course, we have a lot of organic compounds, especially for those of high number of carbon atoms. And we called a huge group of it petroleum, which is a complex mixture of different hydrocarbons that varies greatly in composition. Now, if we look here at this table, we extract the fuel petroleum from the earth as a mixture. And this mixture contains many other compounds that we can take it. And we can extract the compounds from the raw material here, the petroleum, by using fractional distillation. If you look here at this table here, gasoline, which is from C4 to C12, of course, here we are talking about starting from C4 and reach to C12. The boiling point rate for it will be up to 200. And as you can see in this table here, we have kerosene, which is from C10 to C14. The boiling point is from 180 to 290. And then we have the middle distillates, such as heating oil, gas, turbine fuel, and diesel. Then we are talking about lubricants, oil, and wax. And finally, we are talking about asphalt, which is contains more than 36 carbon atoms. Now, the main principle for fractional distillation, guys, here is that we can use like Okay, this is just to understand the process here. Here we put the raw material, petroleum, with heat here, we increase the temperature. Now, the temperature here will be very high. If you look at the asphalt, we said, let's assume that it will boil over 600. So the temperature here will be, for example, 600. Now, as we're going up away from the heating source here, the temperature will decreases. So let's assume that here we have the temperature here will be 400, and here will be 300, and the temperature here will be 200. And as we're going up even more, the temperature will be this. So all petroleum here will be boiling and moving to gas. Now, once the gas reaches this point here, the products that boils below 400 will start to distillated here, and we can gather it and take it outside. So for example, if you look at wild gas and lubricants oil, it will be here converted to liquid because it boils over 400, and below 400 it will be liquid. So we can extract it here. The other compounds are still boiling and they are in the gaseous state. And so when we reach this level here, the 300, we can extract other type and so on. And finally, we will have asphalt staying here because it boils over 600, so it will stay in its liquid state. This is the main principle for fractional distillation. And as you can see here, this is the fractional tower in petroleum refineries. They use the same principle we explained before. Now, what about the other type of hydrocarbons, which is the unsaturated hydrocarbons? And remember that we said we have two types of hydrocarbons: saturated, which means the hydrocarbons that contains only a single bond, and unsaturated hydrocarbons where we could have double or even triple bond between the atoms. So unsaturated hydrocarbons are hydrocarbons in which not all carbon have four single covalent bonds. So we will have double and triple bond. And as a start, we're going to talk about alkenes. Now, we said that we have alkane, which means single bond. Now here guys, we are talking about alkene, which is E, which is double bond. So we could have a compound like C, double bond C, 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 and remember that each carbon atom should form four bonds. Now this carbon here already formed three, so it will take only one bond. And this one here, it will not contain three hydrogen atoms like this one here because it's forming a double bond with the neighbor carbon atom here, so it will take only two hydrogen atoms. Now, naming of alkenes is just the same as naming of alkanes. We're going to follow the same rules, but the longest chain we're going to choose here must contain the double bond. So we have to count the number of carbon atoms with the longest chain that contain the double bond. And we're going to replace A in E with E in E. So for example, if we have this compound, Let me replace this one. Let's try to find out the longest chain here. We have to start from this side. 1, 2, 3, very short. 1, 2, 3, 4, 5, 6. This is a chain. Or 1, 2, 3, 4, 5. This is another chain. Or 1, 2, 3, 4, 5, 6, which is same as the first one. What about this one? 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. Now we can't take this one because it is not containing the double bond. So the double bond must be included within the compound. Another example. Let's count this one here. Remember that this double bond must be N. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So can we take this chain, for example? What about this one here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here we have the longest chain. But we can't take it because it is not containing the double bond. So the double bond must be exist in the longest chain. So 1, 2, 3, and 4. This is the longest chain, for example. Now, numbering for the carbon atoms here, instead of making the branch take the priority to have the lowest number, here priority will be given to the double bond. So the double bond must have the lowest number. So we have to start counting from this side here, not from this side here. So 1, 2, 3, 4, 5. 5 means that we are talking about pent. Same thing, prefix depends on the number of carbon atoms. Now, instead of using A in E, we're going to add E in E to have pentene. And we have a branch here. So we have 2 methyl pentene. But when we are talking about pentene, what is the location of the double bond? So we have to mention the location of double bond, which is located or started from the second carbon atoms here. So we have 2 methyl dash 2 dash pentene, and this 2 reflects the location of the E in E here, which is the double bond. For example, here we have 1, 2, 3, 4, 1, 2, 3, 4. We have 4 carbon atoms, so we are talking about bute. We have double bonds, so we are talking about butene. Now, here, as you know, or as you can see, we have the R group here. This is the alkyl group. Remember when we said that If the alkane group lost one hydrogen atom, it will be alkyl group, not alkene. So the alkane group here and this one here, methyl and methyl, they are not at the same level, so we have a trans to butane. While here they are located at the same level, so we have cis to butane, which are geometric isomers as explained in previous lessons. So this could be R, and this we can say that this is R, which is alkyl group, and R, which is alkyl group. Here, as you can see, this is the Bole-Stick model and the structural formula for ethene and propene, transbutene and cis-butene. And notice, guy, that we don't have methane here because we are talking about a double bond. And meth means that we have only one carbon atom, which means that the other atoms are hydrogen, and hydrogen is not able to form double bond. So we don't have methane or one carbon atom with double bond. So alkenes start from ethene. This is another example for naming the compounds here. As you can see here, we can't take this chain here because it is not containing the double bond. So the longest chain must contain the double bond here. We have 1, 2, 3, 4, 5, which is pentene or 1 pentene. Now usually we don't mention the number 1 here if it is located at the first group. So we could say only 2-ethyl pentene. And if we have 2 double bonds, as you can see here, we have double bond here and double bond here. 1, 2, 3, 4, 5. So we are talking about pentene. Now here pentene with 2 double bonds. So instead of saying pentene, we have to say pentadiene to show that we have a double bond, or even a triene. So for example, if we have C, 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 and C, 1, 2, 3, 4, 5, 6. So we have hexa, and we have 1, 2, 3. So hexa, 3, hexa, triene. And the location of them, if we start from here, 1, 2, 3, 4, 5, 6, we will start from number 1. But the other one, the next one will be 4. But if we started from the other side here, 1, 2, 3. Here we will have 1, 4, 6. But here we will have 1, 3. Sorry, here we'll have 5. And here 1, 2, 3, 4, 5, 6, 7. Oh, this is not hexa even, guys. Sorry for that. We are talking here about 7. So we are talking about hepta, triene, ene. So here we will have lowest number 1, 3, and 6. So 1, 3, 6, heptatriene. Okay, what if we have CH3 here? In this case, the compound will have 5 methyl. So we're going to add 5 dash methyl dash 136 heptatriene. This is the naming system of the alkene. It's very close to the alkane as well. For example, this one, as you can see here, 1, 2, 3, 4, or 1, 2, 3, 4, or 1, 2, 3, 4. But we can't say 1, 2, 3, 4, 5 because we are not taking the double bond. So at all cases, we have 4 carbon atoms. So with one double bond, so we are talking about butene. And the butene, the double bond, we have to start numbering from this side here. So we have 1 butene, and 2 we have ethyl, and the 3 we have methyl. So the compound will be 3 methyl or 2 ethyl. What do you think? What should we start with, the methyl or the ethyl? Remember when we said at our previous lesson that we have to take the alphabetical order. So we'll start with 2 ethyl, 3 methyl, butene, and this will be the name of the compound. 2 ethyl, 3 methyl, 1 butene. I hope, guys, that you're going to solve these questions here to practice yourself for naming system for both alkanes and alkenes. And see you in our next lesson. Bye, God. Thank you and be safe.